So this video is the first one having to do with 8.2, which is areas in the plane. And we introduced this, or I introduced this the day before we started this break. So you might remember parts of it. But let's suppose we have a function, I'll call it f of x, and it's on an interval from a to b. And if I wanted to find the area under this curve between the function f of x and the x-axis, I could integrate from a to b of f of x. Now, let's suppose we have another function, let's call that g of x, and I wanted to find the area under that curve. Well, that would be the integral from a to b of g of x. But if I wanted to find the area between these two curves, I wanted to find this area here, this orange region, what I could do is take the area under f of x and subtract the area under g of x. And what we'd end up getting then is the integral from a to b of f of x minus g of x. Now, if you notice, f of x is the upper function and g of x is our lower function. So what we can remember then is to find the area, all we need is the upper function minus the lower function with respect to x. What we're really doing here is finding the area of an infinite number of rectangles whose height is f of x minus g of x, and whose width here is delta x. And when we sum the infinite number of rectangles here, that's how we get this integral. Now, I'm going to change this problem slightly, and this sometimes throws people off. Let's suppose we have a function, f of x, that is positive on the interval from a to b. And so we know that the area under that curve would be the integral from a to b of f of x here. And then suppose that g of x is taking on negative values here between a and b. Now, the integral from a to b of g of x dx, the area is always positive, but the value of the integral is negative. So if we would add these two integrals together, this area is positive, this area is positive, but the value of this integral is negative. And so if we do this, f of x dx, if we add the opposite of that integral, then we will actually get the combined areas, the one above the x-axis and the one below, because this integral is negative, and if we add its opposite, then we will get the combined area. Now notice, when you subtract a negative, that's the same as, when you add a negative, that's the same as subtracting. So we basically get what we had up above, that it's still our upper minus our lower function, regardless of whether one is above the x-axis and one is below the x-axis. Let's now turn to some of these problems. In number one, we have one function y equals 1, and then we have another function cosine squared x. So we have cosine squared x here, cosine squared x. So if we want to find the area between these, we would take our upper function minus our lower function, And we are going to integrate from 0. And at the right, we're going to integrate to pi. Now, what I'd like you to do is plug this into your calculator. I won't give you the answer quite yet. I'll just go ahead and do that calculation, and then we'll check it in a little bit. Okay. Okay, so for number 2, we have an upper function, which is 1/2 secant squared x, and a lower function, which is -4 sine squared of x. Now, in your book, they used t's here, but when you plug it into your calculator, we're going to use x's. So I'm going to leave these as x's. And here we're going to integrate from -pi over 3 to pi over 3. So if we set our limits of integration here from -pi over 3 to pi over 3, and then let's do that